Watching the sheer volume of sand moving across a dune crest reveals an invisible, low-density fluid reshaping the surface of the Earth. Water is the planet's most powerful erosive force globally, but wind dominates in arid regions that lack vegetation and soil moisture. Air is a low-density fluid, yet it possesses the mechanical capacity to sort millions of tons of solid rock. These Aeolian processes act as a strict mechanical sorting engine governed by rigid fluid thresholds and particle physics. This vast dune field represents the highly ordered terminal result of a geological centrifuge. To see how this centrifuge operates, we have to look past the macro landforms and focus on the microscopic boundary layer where moving air meets resting soil. Transport is initiated at the fluid threshold, the specific, relatively high minimum wind velocity required to dislodge a resting grain from the surface. Overcoming the static friction and gravity of a rock requires significant initial kinetic energy because air has such low mass. Once the sand is in motion, the system shifts to the dynamic threshold, a notably lower wind velocity required to maintain transport. This raises a mechanical question. Why does it take less wind energy to keep a desert moving than it takes to start it? Aeolian transport is a non-linear system. It relies on an initial burst of energy to trigger a self-sustaining chain reaction. This diagram outlines 3 wind transport modes, gated by sediment size. Particles under 0.05 millimeters move via suspension, lifted across vast distances. Grains up to 2 millimeters undergo saltation, bouncing downwind. Larger grains move via creep, rolling along the ground. Saltating grains act as kinetic projectiles, creating a cascade effect that explains the threshold paradox. As these grains smash back into the bed, they dislodge other rusting grains and physically ram the heavier creep grains forward. Saltation drives 50 to 70% of wind erosion, and the resulting creep accounts for up to 25% of surface movement. These mid-air collisions lead to attrition, where grains are chipped and rounded. This gives Aeolian sand its frosted texture and creates the fine dust needed for suspension. The wind uses a fraction of the sand as a kinetic hammer to continuously shatter and push the rest of the landscape forward. It is often assumed that wind reshapes landscapes through abrasion, or violent sandblasting. While abrasion creates visible pitting and features like mushroom rocks, it is geologically insignificant for bulk mass removal. The true architect of desert erosion is deflation, the turbulent lifting and permanent removal of loose, fine materials. Localized deflation continuously excavates fine particles to create massive land depressions known as blowouts. The removal of fine sand leaves behind an interlocking sheet-like surface of angular rock called desert pavement. Aeolian erosion operates by quietly and systematically vacuuming away all the microscopic mortar that holds the ground together. Landforms grow whenever sediment enters an area faster than the wind can carry it away. The wind perfectly segregates sediment by mass over huge geographic areas because of the differences between saltation and suspension. Heavier sand particles move by saltation and fall out of the wind stream quickly, accumulating in concentrated regions called ergs, or sand seas. Silt and clay are carried in suspension for vast distances, often settling far beyond the borders of the desert. These suspended particles eventually settle to form loess, massive, highly porous, homogeneous plains of silt located far from the original sediment source. Because wind is such a strict fluid sorter, there is almost no interbedding or mixing between pure ergs and pure loess deposits. The physical limitations of fluid density turn the atmosphere into a planetary scale sieve, strictly segregating the Earth's crust by grain size. A dune begins when a small pile of sand creates a minor topographic obstacle, disrupting the wind flow. The pile increases aerodynamic drag. Wind vectors compress over the top and expand on the lee side, dropping saltating particles. As more sand drops, the pile grows, creating exponentially more drag in a positive feedback loop. Once the slope angle becomes too steep, the dune collapses under its own weight, causing the entire landform to slowly migrate downwind. These sharp, repeating crests and slip faces are visual maps of the aerodynamic dead zones created by the feedback loop. High-energy fluid thresholds initiate a kinetic cascade of saltation, which strips deflation zones, sorts sediment by mass, and triggers massive depositional feedback loops. The desert landscape is a highly ordered, predictable mathematical output, driven by the strict laws of fluid dynamics and particulate physics.